forth. Number 14 says the equation of the tangent to the curve y equals e to the x ln x when x equals 1. So we want the equation of the tangent to the curve. So we need to find the slope, first of all, so y prime, which will be e to the x times the derivative of natural log, which is 1 over x, and then plus the derivative of e to the x, which is e to the x times natural log x. So if we evaluate that at x equals 1, we ought to get e plus 0, or just e. So we have the slope of e, and if we were to plug the point 1 in, y of 1 should be equal to e times 0, or just 0. So we're looking at the point 1, 0 with a slope of e, which ought to be y minus 0 equals e times x minus 1, which looks like that's choice C. Any questions there on that? Everybody good with 14? All right. Now I know we've done some of these other ones. Did we do 17 yet? We had done 17. Maybe not though. We did 17, okay. Did we do 19? Okay, did we do 20? All right, 22. 31. Oh boy, this is fun. 32. No, we didn't do 32 yet. Oh, all right. Thought maybe we're just going to go through the whole list and I've already done them, and then that'd be easy. All right, 32. We got an integral of cosine cubed x dx. So in order to integrate cosine cubed, we want to rewrite this. Anytime you have an odd power of cosine or an odd power of sine, you want to rewrite it. So one where it's just the cosine or the sine if it was sine cubed, and the other where it's cosine squared. And then we know we can rewrite cosine squared using the Pythagorean trig identity as 1 minus sine squared. So we're just going to make this an integral of cosine x times 1 minus sine squared x dx. And if I let u equal sine x, then du is cosine x dx, which I have. And this just becomes the integral of 1 minus u squared du, which is u minus u cubed over 3, plus a constant. And if u is sine, that's sine x minus sine cubed x over 3, plus a constant, which would appear to be choice C. Everybody good there? I think we're all good. Yeah, I don't think anybody's upset. Although I might be the one that's causing some of this strife here with my. I've returned. I've returned to my classroom, which means that my children can't hear all the things that I say now. So it's a dangerous line here that we're going to be treading on. Gotta be careful. Everyone good with 32? Okay, 36. I think we did 36, but I could be wrong. Did we do 36? We did, okay. What's the 41? Did we do 41? No, another no. Oh boy, all right, 41. Exciting. 41. Okay. We did some like this back when we did one of the other sets of multiple choice problems. So, but we'll do it again here. We're going to make the substitution that x equals tangent theta. And we want to figure out what is equivalent to the integral from 0 to 1 of root 1 plus x squared dx. This is not something I would expect them to ask you on the AP test. This substitution that they have you do here is called an inverse trig substitution. And it is something that you do in BC or in a second semester of calculus. Now they're just trying to see if you can manipulate this integral with this substitution, which is an AB type topic. But actually needing to do that and then evaluating the integral once you've changed it into terms of theta, and knowing that this is the right substitution to use to solve this integral is not something you need to know how to do. You just need to be able to plug it in here. So this becomes the square root of 1 plus tangent squared theta. Dx, though, we need to figure out what that is. Dx is the derivative of tangent theta, secant squared theta d theta. And then our integral, well, if this was an x value, then we need to know when does tangent theta equal 0. That'd be when theta is 0. And we need to know when does tangent theta equal 1 for our upper limit, which would be at pi over 4. Oh, that's not a good looking 4. That's better. And so the square root of 1 plus tangent squared theta, well, 1 plus tangent squared theta is secant squared theta using Pythagorean trig identity. And if this is secant squared, the square root of secant squared is just secant. And secant times secant squared is secant cubed. So we should get that, which looks like it is choice, what is that? Choice D. Very exciting. Any questions there on that one? And if you happen to be looking through, just for fun here, if you happen to be looking through and looking at the PDF right now that I posted, in the BC only section, there's question number 51, which is you have to use an inverse trig substitution similar to this one to solve that integral. So in that one, they don't tell you how to deal with it. They don't tell you what substitution to use, but you got to turn that integral into an integral in terms of theta using an inverse trig sub. But that's something you'll all learn the next time you take another calculus class. Exciting. All right. Next one was 65. Do we still need to do 65 or do we do 65? We did 65, okay. 68. We did not do 68. Okay. All right, let's do 68. The volume in cubic feet of an inner tube with an inner diameter of 4 feet and an outer diameter of 8 feet. Okay, inner tube. So you guys know what I mean. You know what an inner tube looks like, right? An inner tube is just like a donut, right? A big thing you blow up. So we got to think about sort of what exactly we're doing here. So let's put something on an axis here, and yeah, sorry, this is 68. We want the inner diameter to be 4 feet. So we're going to be at 2 and at -2 here. And what I'm going to do is, what do we want the outer diameter to be? 8. So from 2 to 4 and from -4 to -2, if I were to sketch a circle in here and revolve that circle around the y-axis, I can't draw a very good picture of that because I'm just not good at doing that sort of thing. But if we were to revolve this around the y-axis, bring it out of the screen and back into the screen, we should get an inner tube, a big donut that has an inner diameter of 4 and an outer diameter of 8. And so from there, we should be able to figure out what the volume is by writing an equation of this circle, because this is just a circle with a radius of 1 and a center at the point 3, 0. So we should know that this should be the circle x minus 3 squared plus y squared equals 1. And if we were to, let's say, take just the top of this and revolve it around the y-axis, that should give us half of the volume, and we could just double it. And it seems to me that the easiest way to do that, if we're going to revolve it around the y-axis, would be to do it in terms of a shell. And so we're going to just do the top half of it. So that would be the function y equals the square root of 1 minus x minus 3 squared. And I don't know. We'll see if we actually need that in a second here. But what we'll do is do 2 pi times our radius, and our radius should just be x, and then our height should just be square root of 1 minus x minus 3 squared dx, and we're integrating that from 2 to 4. Yeah, that's not going to work out so nicely, is it? That's a bummer. Let's see. Let me think about it. Is that going to work? Or if it'll be better for us to do it in terms of y. Yeah, I mean, it'll work out. We can do it in terms of y also. Let's think about it in terms of, if I were to do it in terms of y, we're taking, we've got a, we're going to, let's do it in terms of x. I like this better. So let's do a substitution where, no, I don't like that substitution either. Yeah, I was thinking to do the x minus 3 sub, but subbing out the x minus 3 becomes a little bit of a problem. Well, let me see. If we do x minus, well, let's try it. If we let u, we're going to have to do 2 substitutions if we do it this way. Otherwise, we might have to turn around and do it in terms of y. But if we do u equals x minus 3, that's going to give us the square root of 1 minus u squared. Yeah, yeah, that's not going to quite work out how we want it to, because that's going to give me x is equal to u plus 3. So I'm going to have a u plus 3 here, which is fine. I don't feel like converting this at the moment, so I'm just going to write x equals 2 and x equals 4. I guess I can convert it. Let's convert it. X is 2, that's negative 1, and if x is 4, that's positive 1. Yeah, so here you'd have to do, let's see, dx is just du, so that's just du. So here you'd have to let u equal 1 minus u squared. Du would be 2u, but you don't have a 2u, you have a u plus 3. Which is going to create an issue that you're not going to be able to deal with until you get to Calc 2. So, oh, good, I found it. All right, so instead of doing this in terms of x, which is what I was hoping we could do using shells, we won't be able to do that without without some second semester calc stuff. So, let me go to a new page here. I'm going to sort of resketch this here. There's my circle. It's got its center at 3, 0. It's got its radius of 1. And what did we have? We had x minus 3 squared plus y squared equals 1. So instead of solving this for y like I did to try and do it the other, let's solve it for x. And we'll try to do this just using a different method here. So if I solve this for for x, I get 1 minus y squared, and then I got to square root it, and then I got 3 plus or minus that. So this is what we should get for x. And let's see, if we're going to take this around the y-axis, let me think about a good way to do this without using Calc 2 stuff. No, we gotta do this. So what we'll do is if we think about this is 2 different functions here. So one of them is 3 plus the square root of 1 minus y squared, right? And so that function, what part of this semicircle is that? It ought to be the right half of it. So if we talk about just the plus, that's a different color here. If we talk about just the plus, that should be this side, and then just the minus should be this side. And so the outer radius, if we're revolving the red part around around our y-axis, our outer radius. Let's see here. Yeah, it's gotta be, yeah, okay, that makes sense. It's gotta be done in terms of y. So our outer radius should be 3 plus 1 minus root 1 minus y squared. So that's our outer radius. And then our inner radius ought to just be this line of 3. And that's going to require us to do that from 3 to 4. Pi out in front, and we'd have to add to that the green part, which would be pi times an integral from 2 to 3 of 3 squared minus 3 minus root 1 minus y squared dy. Which both of those also require a second semester of calculus to do. Maybe this one was just supposed to be marked as a BC only problem and it wasn't. Yeah, I think that one was supposed to be marked as a BC problem. Well, they're not actually that difficult. I mean, there's a standard formula for the volume of these are mathematically, these are called toruses. tori, I guess. I don't know. There's a very simple formula to find the volume of any torus. It's, if I remember correctly, it's just pi times the inner radius squared times 2 pi times the outer radius, I believe. Yeah, we're going to go ahead and say that should have been a BC problem because I don't see a good way to do that one solely using AB material. Unfortunately, I think they might have screwed up, or there might be something that I just don't see offhand. But I wouldn't expect to see a problem that was as difficult as that in the regular AB multiple choice for sure. So feel okay if you didn't figure that one out because that should have been a BC problem. What was that one? Was it 65 or was that 68? That was 68. Okay, so the next one, Dylan, you asked for 71. Did we do 71 yet? No? Okay. No. So 71. We've got x is greater than 0. We got the derivative of f of x is g of x. We got the derivative of g of x is f of root x. That's fun. And the second derivative with respect to x of f of x squared is what we're looking for. Oh, that's a fun thing. All right, so let's see here. So let's try and figure this out here. We're looking for the derivative with of the derivative of f of x squared. So we're looking for the derivative with respect to x of the derivative with respect to x of f of x squared. So the derivative with respect to x of f of x squared, well, to take the derivative of f of u, f of a function, it should become f prime. So I'm going to keep this derivative with respect to x out front. It should be the derivative with respect to x of this inside piece should be evaluated as f prime of x squared times the derivative of x squared. So that should be 2x times f prime of x squared. And f prime, as we said before, the derivative of f is g. So now what we're looking for is the derivative with respect to x of g of x squared times 2x. So in order to figure that out, we need to use the product rule. So that should be g prime of x squared times the derivative of x squared, which is 2x, times 2x, plus g of x squared times the derivative of 2x, plus 2g of x squared. So that should be 4x squared, and then g prime was f of root x. So g of x squared, or sorry, g prime of x squared ought to just be f of x, and then plus 2g, oh man, the handwriting got bad there, plus 2g of x squared. So let me write this again up here. It should be 4x squared f of x, plus 2 g of x squared. Does that conceptually makes sense to everybody or no? All right, and then 74. Did we do 74 or no? Okay. All right. Cool. All right, so yeah, I'm onto your list of questions here that you had. Number 1, did we ever do number 1? No. Okay, number 1. Which of the following functions is continuous at x equals 0, right? And then they give us a bunch of different functions. So continuous at x equals 0. So first one they give us is sine of 1 over x, or 0. This is if x is 0, and this is for x not 0. So is this continuous? Well, if I try to look at the limit as x approaches, right? Well, actually, before I even start saying that, to think about if something is continuous at a point, the limit has to exist. F of, we'll say 0, has to exist. And the limit as x approaches 0 of f of x has to equal f of 0. Those are the 3 criteria for a function to be continuous at a point. So first off, does the limit as x approaches 0 exist? Well, that's the sign of infinity. Sign of infinity, well, can't take that. It just oscillates back and forth forever. So for number 1, for A, the limit doesn't exist for the first choice, so you can't do that one. B is the greatest integer function, so we should be familiar with that. It looks like this. The limit as we approach 0 doesn't exist for B. For C, we've got x over x if x is not equal to 0. And we got 0 if x equals 0. Well, this is always 1, so this should look like 1 no matter what, except at 0 it's 0. Well, definitely not continuous for C. Real quickly, I mean, it looks like the answer should be D, just based on the two I'm looking at. So we'll look at E real quick. At E, the limit as x approaches 0 is undefined, right? E, that limit doesn't exist. X plus 1 over x as x approaches 0. That's 1 over 0, which is undefined. So the limit doesn't exist. For D, we've proven using the sandwich theorem that the limit as x approaches 0 of x sine of 1 over x is 0. We've proven that a few times during this course of the year. And it says that f of 0 is also 0. So that one must be continuous. Does that make sense? Cool. All right. That's not what I meant to do. Let's try this again. All right. Let's see. 19 we did. 25 is on your list, but I don't see it right here above, at least on Dylan's. Did we do 25? Ever? No? I can get the pages of my book to stop sticking to each other, and we can do number 25. All right. 25. So 25 says the general solution to dy dx equals 1 minus 2x over y is a family of, and then it gives us a bunch of different options for what that might look like. The best way to figure that out is just to separate the variables. Y dy equals 1 minus 2x dx and see what the solutions are. And we get y squared over 2 equals x minus x squared plus a constant. The plus a constant's not really going to matter much. But we'll multiply by 2. Plus some other constant, we'll just call it 2c. And y is the square root of 2x minus 2x squared plus that constant. Well, that's not real helpful because we probably don't know what that looks like. So if we don't go all the way here, solving it to y equals, since that's not a function we're familiar with, we should at least be able to look at it when it looks like this. We can make it 2x squared plus y squared minus 2x equals that constant equals 2c. And hopefully, with any luck, we're familiar with what that is the equation for. And this should be the equation for an ellipse. right? Because this doesn't turn out to be a nice circle. The coefficients aren't 1 on both of these, but it's still of the same form. Yeah. Ax squared plus by squared minus cx plus dy equals some constant, and that's the form for an ellipse. So these should be ellipses. If it was a minus between the two terms, those would be hyperbolas between the powers, like x squared and y squared. That'd give you hyperbolas. Parabolas and straight lines you get to see because it'd be linear or just a squared function. Everybody good there? Any questions with that one? Does that make sense? Yeah. Okay. 30 was on your list. I remember doing number 30, but I don't know which class period it was in. Did we do 30 already? No? Okay. Guess I did it in second period. All right, so number 30, we want to know the number of values of k for which f of x equals e to the x and g of x equals k sine of x have a common point of tangency. Right? So basically what we need to do is figure out any points that the two functions go through the same point and also have the same slope at that point. And so in order to figure that out, we first should be able to set them equal to each other just to see k sine of x equals e to the x, we'll say. And then we also need to figure out when do they have the same slopes. So effectively, when are the derivatives of each of them the same? The derivative of f of x is e to the x, and the derivative of g of x should be k cosine x. So we are looking for what values, for what values both of these equations are true. So for what values of x and k are these both true? Well, that just means we need to solve a system of equations. And since they're both equal to e to the x, we can just set the k sine x equal to the k cosine x, cancel out the k's, and say, well, this occurs, these things have common points of tangencies whenever sine of x is equal to cosine of x. Well, when is sine of x equal to cosine of x? There are no restrictions on the values that they gave us. So this happens an infinite number of times. Sine x equals cosine x at pi over 4, and at 5 pi over 4, and at 9 pi over 4, and at 13 pi over 4, and at 17 pi over 4, and at 21 pi over 4, and so on. Does that make sense to everybody there, number 30? All right, 31, I know we've already done. 39, have we done? Did we do 39 already? No, didn't do 39. Okay. All right, 39, we're looking for the domain of the particular solution for dy dx equals 6x over x squared minus 4, containing the point where x equals -1. So in order to figure out what this is, first thing we're going to need to do is we're going to integrate it. And we should be able to integrate it pretty easily. We'll just let u equal x squared minus 4. du will be 2x dx. So I'm going to have a 3 left over. So we'll put a 3 outside my integral. And then it becomes an integral of du over u. So y equals that. We got y equals 3 natural log absolute value u plus some constant. Everybody good with that so far? Hopefully. Okay. And so then we can look at this and say that the domain of this is, if we're looking at the absolute value of x squared minus 4, that means that x squared minus 4 cannot equal 0, which tells us that x cannot be positive or negative 2. And since our solution needs to be valid for x equals negative 1, we have to look at only the continuous piece that includes x equals negative 1, and that's from negative 2 to 2, which looks like choice C. Good or no?
Good.
Wonderful. All right, let's see. 60. Did we already do 60 any time during any of this? No. All right. So 60, we've got y equals the integral from 3 to x of 1 over root 3 plus 2t dt. So we want to find the second derivative, so dy dx to begin with. If this is the derivative of an integral from a constant to x of a function, it should just be that function in terms of x, so 1 over root 3 plus 2x. And so then the second derivative should just be the derivative of that, which we could use the quotient rule or the reciprocal rule. So the reciprocal rule says this should just be negative derivative of the denominator. So that should be the derivative of root 3 plus 2x is 1 over root 3 plus 2x times the derivative of 3 plus 2x, which is 2. And then we need to divide that by the denominator squared, so 3 plus 2x. So we end up with negative 2 over 3 plus 2x to the 3/2 power. I don't know if that's how they wrote their answer, but let's see. Negative, yeah, that is how they did. Negative. Except I have a negative 2 up there, and they have a negative. What did I say the answer choice was for that? Oh, when I took my derivative here, this is 1 over 2 root of that, so the 2's cancel. Made a stupid mistake there. Remember that the derivative of root 3 plus 2x is 1 over 2 root 3 plus 2x times the derivative of 3 plus 2x. They should get that. Everybody good there? With 60? Oh, good. 65, we already did. 67, did we do 67 yet? No. Okay, 67. The integral from 0 to 3 of f of x plus k is 4. We want to find the integral from k to 3 plus k of f of x dx. Okay, so I think what I would do here is I would let u equal x plus k in this. If u is equal to x plus k, then du is just dx. And when x is 0, this lower limit should just become k. And when x is 3, the upper limit should become 3 plus k. And it just becomes f of u du. And we've basically just said that this is equivalent to this. So that must also equal 4. Good or no?
Wait, could you say that last part again for a sec?
So yeah, we just did the u substitution. I just did a u substitution, let u equal x plus k. And that doesn't, that doesn't change the value of this integral. And when I did the integral, or when I did the substitution, u equals x plus k, du is just dx. 0 becomes 0 plus k, okay. 3 becomes 3 plus k, right there. So effectively, I end up with this. Without the equals 4, I just have the integral from k to 3 plus k of f of u du. Well, that's what we're looking for. That's what it asks, right? It asks for the integral from k to 3 plus k of f of x dx. Doesn't matter what this variable is. Right? I could put a theta, I could put a alpha, beta, kappa, whatever in here. This integral should be equivalent to this integral, because when I did the u substitution, I got the exact same thing. Does that make more sense now or no?
Yep, thanks.
All right, 67. Let's see, what was the next one here? Let me take a look on my phone. 68, we already did. 71, we already did. 74, we already did. 78. Did we already do 78 sometime? We did, okay. 81. We did not do 81, okay. Cool, my pen's not working. There we go, 81. So this table is giving us speed at 0, 1, 3, 6, 30, 22, 12, and 6. And it says, let's see, estimate the acceleration at t equals 2. Okay, well, if we want to estimate our acceleration at t equals 2, this is, they've only given us the speed, which is poorly worded. My guess is the best thing they want you to do is just do 12 minus 22 over 3 minus 1. So negative 10 over 2, or negative 5, choice C. Just average rate of change. Good or no?
Yeah, good, thanks.
Yep. All right, then next one was 83. Had we done 83 already or no? No? Okay. So 83, we're talking about a population of deer. It increases at a rate of dp dt equals k times 1,000 minus p, which tells us that this is an exponential growth for dk. So it says it's increasing, so exponential growth. And it says if 300 deer were originally placed in the area, and there were 500 after 5 years, how many will there be after 10 years? So this is one where you're going to have to go through and solve this differential equation. So it's really similar to some of the potato and the baby bird, and there was another one of those that we did also. I think it was the trash problem. Yeah, so dp over 1,000 minus p equals k dt. So this is negative natural log absolute value of 1,000 minus p equals kt plus our constant. And our initial condition was that there were 300. So negative ln of 700 equals our constant. So we end up with negative natural log absolute value of 1,000 minus p equals k t minus natural log of 700. And we want to know, what do we want to know? It had grown to 500 after 5 years. So negative natural log of, if it grew to 500, that means this is now 500 here. It's 5k minus ln 700. If we just plug those values in, that gives us ln 700 minus ln 500 equals 5k. Ln of 700 minus ln of 500 is ln of 700 over 500, or ln of 7/5. And then divide that by 5 to get our value for k. And then from there, you'll just go back and you've got negative natural log of, what was it, 1,000 minus p equals 1/5 natural log of 7/5. That's our kt, or k, times the t, minus natural log 700. And so it says find the population when the time is 10. So if I plug in 10 here, that'll become 2 ln 7/5 minus ln 700 equals negative ln absolute value of 1,000 minus p. And then it's just a matter of doing arithmetic. So you'll figure out what 2 ln of 75 or 7/5 is. Subtract ln 700 in it, divide by a negative 1. So we'll just put a negative out in front of all of this. We're going to exponentiate it all, which will get rid of that. So it'll be 1,000 minus e to the negative 2 ln 7/5 minus ln 700. And I don't know what that comes out to be, but it must come out to be something, one of those numbers there. Anybody know offhand what it comes out to be? No, I can. The book says what? What does the book say? The book says that's about 643. Any questions there on that one? Everyone's good or no? Yeah? All right, last one. Number 93. Did we do 93 already? I remember doing 93, but now I don't remember if it was this class or a different class. Oh, we did. Wonderful. All right. That's it.